My name is Rajeev. I'm working as a project researcher in Laboratory Studio. The title of my presentation is Design Ultra-Fast Basal Beam, an efficient tool for laser structuring. So these are the outline of my work. Let's start with the ultra-fast laser for 3D bulk modifications. It has been shown that in the recent works that tightly focused ultra-fast lasers can facilitate precise structuring inside transparent bulk material. That is, they can structure on the surface as well as inside the transparent bulk materials. And it leads to so many applications like optical data storage, and also we can have the waveguide inside the photonic crystals. However, when we are trying to create the waveguide inside the photonic crystals, whenever we are using the conventional techniques, they are limited by the diffraction. So we cannot actually make a high aspect ratio 3D nanovolumes with a single shot laser. So to perform it, we need a beam which is non-diffracting in nature. So here comes the basal beam. Basal beam is a non-diffracting field which can be generated by the hexagon. Hexagon mainly introduce a conical face into the face of the plane face of the incident field, and it can produce an extended depth of focus. This extended depth of focus can be used to create a 3D bulk modification of higher aspect ratio. This aspect ratio has been reached to the order of 100, and it can also use for having efficient technique for the glass cutting. In our experiments, we worked with this sapphire where we got two types of 3D bulk modification. One is the amorphous and other one is the cavity. As you can see here, this is the amorphous region and this is the cavitation. So in this cavitation, as you can see that the size is of the order of 100 nanometer. However, this size is circular because the basal beam which we use is circular in the ideal condition. So if we wanted to tune the size of this cavity, we have to tune the shape of the basal beam. So one type of tuning is to create the elliptical basal beam. To create an elliptical basal beam, the convenient technique which we shown in our recent publication is that we can use the mask to we can put the filters on the symmetric face of the hexagon. Two type of filter we discussed. One is the rectangular face and other one is the thumb face, or you can say a hourglass or butterfly face. So these creates elliptical lobes at the center of the field, as you can see here. And in the recent publications, it has been shown that the rectangular face can actually used for creating the elliptical nano channels. And also, if you increase the intensity, you can even get the multi-channels at a single shot. Also, second is the modification of the longitudinal intensity profile. So let's first understand how this intensity profile is generated in the ideal case. When you have a Gaussian profile at the incident plane, you can just divide it into some circular lines in here. So each circular lines is corresponding to each point on the propagation distance. So if we wanted to modulate this intensity profile, we can just put a mask on in front of the hexagon so that we can block the intensity. Like in this case, we are trying to block the intensity which is creating this peak. So we can switch the peak by just blocking the central part of the hexagon by a filter of size D. So these are the results which are produced by the MATLAB. So here you can see we are successfully created modified longitudinally basal beam with changing the size of this filter. These are the images which created by the MATLAB, and this has been used in the recent publication. People have shown that this can be used to control the modification in the photonic crystals. So second is that when we can control the size, but in the earlier slide I shows that there are two types of modification. One is the amorphous and one is the cavitation. So when we are getting amorphous, when we are getting cavitation, to understand this, we have to understand the journey of ultra-fast laser modification. So this is the journey of the ultra-fast laser modification. This whole happens in like 1 microsecond range. For that, we perform pump and probe experiment to have the time-controlled microscopy. So these are the results which we observe. One is the femtosecond range pulse, and second is the picosecond range pulse. So in this video, you can see PCM images with different time delays between the pump and the flow. So here you can see in the beginning, you have this bright region. In a phase contrast imaging, bright region means reduce in the refractive index. In this case, it is the presence of the plasma. In the beginning, we have the presence of the plasma, then we have the heating, and then we have the cooling effect, and then we have the permanent structure, which is amorphous in this case. And also you can see, like in the case of the amorphous, the quantity phase contrast microscopy, which we use because phase contrast microscopy is qualitative. To make it quantitative, we use quantitative phase contrast microscopy. So here you can see it is around 0.03 delta N, that is change in refractive index. So this is in the case of the 1 picosecond. So if you see in the case of the 1 picosecond, in the beginning, this bright region is for the longer duration. Let's see in the quantity phase contrast microscopy. If you compare these two, this time plasma remains for a longer duration, let's say 20 nanoseconds, after which we have heating effect, and then we have cooling and the void formation, which we see by this M. And in there also you can see that the heating is almost double. And then this is how we can see, like in the case of the femtosecond, we have the amorphous, and in the case of the picosecond, we have the void formation. So what we discussed the basal beam shapes and their application in laser structuring. Also, we discussed that basal beam can fabricate high aspect 3D nanocavities inside transparent bulbs. We see that the pump and probe experiment reveals the journey of 3D bulb modification. Also, we observe that in Sapphire for femtosecond pulse, we are having amorphization, while in the case of the picosecond pulse, we are getting the void generation from the center of the amorphous. And then we are able to structure nanocavities of around 100 nanometer size inside the transparent bulb. Thanks, my team. Thank you.
Thank you very much. Are there questions from the audience?
The kind of materials that you're using, maybe it's a naive question for you, but could the technique be adapted to different kinds of materials? So could it be used, for example, for fabrication, or can you tune the dimension of the cavities that you're getting?
The dimensions, yes, actually, dimension because the size of the basal beam depends on the size of the incident field. So if the size of the incident field we can reduce or like make bigger, then the size can be smaller or bigger.
And the material?
Material, actually, whenever we are talking about the bulk modification, we always take transparent material like dielectrics. We are talking about them because I think in the metals and other, it's not easy to structure itself.
What is the maximum aspect ratio that you can reach?
Recent studies have shown that it can reach up to 100.
Oh. Are there any other questions from the audience? Yes, Cory.
Face mask to shape the laser beam.
Yes, that's one.
And then you spoke about the Novak mask. Is it a Novak mask plus a face mask, or is it just?
Yes.
Okay.
Yes.
This one.
Yeah.
This one are face mask.
Yeah. And this is not a face mask. We are using a face mask for an experiment, but you can also use a simple filter, simple blocking, like rectangular block to block the beam of that direction, because it is making it asymmetric. That's why we are at the end, we are getting an effect of astigmatism.
Okay, that's not a mask. That's the face of the laser.
Yeah. No, this one, the first one is the symmetric face, which you put on the SLM, and we can just add a face of a rectangular block plus the face of the cone, just combine them and then we can fix it.
I think we can move on to the next speaker. Thank you very much.